even if you have never worked with FPGA before, when following this video step by step, you will be able to do this. In this video, we are going to create a microcontroller inside of an FPGA, and we will run the microcontroller code from DDR3 memory. For the same FPGA, we are going to write also a standard FPGA code to create a logic circuit, and this logic circuit will be connected to some switches and LEDs located on the board. Then inside of the FPGA, we will also create a logic analyzer, and we will connect the logic circuit to the logic analyzer and also to the microcontroller. Once we will finish all the code for the FPGA, we will also create software for our microcontroller. The software will be able to read status of the LEDs and switches, and the software will also be able to send a message, "Hello world," from our FPGA to our PC through USB UART. And we are going to do everything this within 1.5 hours of this video. I'm not an expert for FPGA, so I called Adam Taylor and he will explain everything. This is the recorded video with Adam, and he will start with talking about what we are going to do and what we will need. So here is my call with Adam. So we need this software, Vivado software, and we are going to use what board?
So we have this Vivado software. We're going to use this ARTY S7 board. S7, it's an S750. It comes in two flavors, a 25 and a 50. It's just the amount of logic in the FPGA. So this is the board we're going to do. What we're going to do is we're going to create a MicroBlaze system, which is a soft MicroBlaze processor. You can't focus, it doesn't focus too well, but you'll see that there's the FPGA here. I'm taking full static precautions, of course. There's the FPGA here. There's DDR3 here. So we're going to create an embedded system that runs from that uses the MicroBlaze to run its programs from the DDR3 memory.
Wow.
To prove that we can get the DDR3 up and running and talking. We've got a little USB UART here that we're going to be able to, well, this has got the JTAG and the UART on it, so we're going to program the application over this, but we're also going to get it to send back a little hello world message just to prove that the processor's up and running. And then I'm going to show you as part of this as well, not everything in FPGA world has to be done using softcode processors, so I've created a little FPGA, a really simple state machine that we're going to put in there as well with the processor, so it's running in parallel with the processor. And that's going to allow us to control these switches it's going to allow us to use these switches across the bottom to control one of these tricolor LEDs on the bottom. So we'll be able to use one of the switches to enable and disable, and then we can mix the colors to create different colors.
Cool.
The other thing we've got in there is, that's not the most exciting thing, but I think it's just a little simple example to show people. But I've also put an internal logic analyzer in the FPGA connected to these switches. So we can talk a little bit about how you debug and what you would do if things weren't going quite as you wanted them to go. So as you can see how it's going to work. And feel free to ask questions as we go through and
I will.
So we're going to use Vivado. And in Vivado, we're going to create the actual application, the FPGA application, so the programming bit file that gets put into the FPGA. We're then going to use a program called VITIS, which is going to create as the application software that's going to run on the
microcontroller.
That's going to run on the microcontroller and connect to it. So what we're going to do, we're going to click Create Project. I've noticed Vivado is always slow when I share my screen, and we're going to do this. So we're just going to create a project. We're going to tell it that we want an RTL project at this point in time, so a register transfer level project. So it's going to be a VHDL or a Verilog project. I don't really have any FPGA pre-written modules that I want to pull in. So we're going to leave that tick. I'm going to tick the board. So one of the nice things about Vivado is it's actually board aware, and I'm going to show when we create this, we're going to use the board aware capabilities of it quite a lot. So we've got the boards. We're going to select the vendor, which is Digilent, and then we're going to find the ARTY S750 down here. click on next. And then it's just going to create as a project that's got targeting the RTS 750 with that particular device on it. But it knows, the nice thing is it knows that it's about, it knows what's provided on this board as well.
That's cool.
So it knows about all the
so you don't have to
peripherals, the
set up everything
memories
from scratch.
No, so when we were talking last time, and we created that PCIe system, and I was showing you how you could pull things on and off to the board. But then I caveated it by saying this has just been pulled together very quickly. I'm not going to guarantee it's going to work. What we're going to do this time is we're going to pull it all onto the board, and I'm going to show you just how easy it is to get it working. And so when we come into this environment, we've got the project manager type environment that we can see. We've got design sources under here, simulation sources, constraints that we'll talk about in a little while. You see, we've got nothing under nothing under any of them. So we're going to get started, and we're going to create a block design. And we're going to create this in the part of the tool called IP Integrator, which gives us that ability to put the blocks together. And use the IP blocks and use the capabilities of the board.
So this is basically based on our board. It's going to kind of add some packages which we can then easily use when we will be creating our software.
So if you see here, we've got this tab across the top. The most interesting one is we've got this board definition, and you can create this for anything. It's just an XML file essentially that gets. So if you created your own custom board design, you could create an XML file that did this as well. And you can see it knows all of the clocks, so about all of the configurations for the DDR3 controller. We're not going to use it, but the QSPI flash that's on there as well. And then it knows all about the LEDs and the switches, the I2C that's present, the PMOD connectors that are present down the side, the reset and the UART.
So if there would be Ethernet, as I mentioned on maybe my board, I would.
It'll be. You should see that there, and then you drag it across. What we're going to do is we're going to make a start. We're going to start with this block diagram here. And this is a block diagram that we're going to create everything in today. So we're going to put the MicroBlaze processor in it. We're going to put the DDR3 controller in it. And I'm going to step you through what we're doing, and we're going to put our custom RTL in it. I've already pre-written the RTL just to prove that we know it's right, but I'm going to talk you through what I did there to create it as well. So the first thing we're going to do, this board's got a couple of clocks on it. It's got a couple of clocks on it. We're going to pull the system clock onto the board.
You always need to put their clock as the first thing. I guess everything needs clock.
Everything generally needs a clock in sort of logic design and synchronous logic design. And there's a reason I added the clock first. So this is just a clocking wizard, and it's going to take in the system clock, which on this board is 12 megahertz. So you can see it actually knows what pin on the FPGA it's connected to. And then we go to the clocking options. You can see that it's 12 meg on this board. And what we're going to do is we're going to turn on both these. We're going to turn on. Actually, we're not. We're going to turn on. We can turn on other clocks if we want. But what we're actually going to do is we're going to change this one to 200 megahertz. And we're going to hit enter. And we're going to leave everything else. We're going to leave everything else as is. So this is going to basically use the clock management tiles in the FPGA to take in that 12 megahertz clock and then create a 200 megahertz clock.
Can you use any frequency? Like you change it to 200. Can you use, I don't know, 213 or something?
Well, let's try.
Okay.
So it's thinking about it. What's it doing? Come on. So it'll tell you that it can't because
so it has to be some kind of multiplier of something. Okay, I see. It says actual. Okay, I see. Perfect.
It says the actual. It says the actual against the. There are some options that you can use, so you could change it to perhaps be a PLL, not an MCM. But if we change it to be a PLL, you'll notice that the input frequency is too low for that PLL configuration.
And the clock input, I guess that's what is connected to Crystal or something, correct?
Yeah, so it's just literally connected to where is it on this one? it's connected to a little if you look up in the top there, you can see, maybe if it focuses, you can see it's connected to that. There's a little crystal.
And in the table down, you actually put there the value of the crystal or oscillator which is on the board.
It actually knows from that XML file, so it was automatic.
But if you have your own board, I guess that's what you. Okay.
Yeah, you would put that. You would put that in. You would change that tick box there to manual, and then you'd change the frequency.
Okay, perfect. I understand everything.
So we want this to pop out at 200 megahertz. We don't want to do anything clever with duty cycles or phase or anything like that. We just want 200 megahertz, please. So that's what we're going to do. We're going to click on that, and it's going to give us 200 megahertz. The next thing we're going to do is we're going to bring the DDR3 on. I'll put the DDR3 on.
So our microcontroller is going to use this DDR memory for something?
Yeah, so the application of the microcontroller can run from, so the FPGA has block RAMs in it. It has a number of block RAMs. So you can configure the microcontroller to run from the block RAMs, and I'll show you how to do it. Or it can run from the DDR. Now, if you run from the block RAMs, you're limited in program size because you've got maybe 32 or 64 KB of memory. However, the other times it runs from the DDR. The other time, obviously, if it runs on the DDR memory, you can have a much bigger program. However, the trade-off comes in if you want to just run it from the DDR, if you want to just run it from your program from the block memory that's in the FPGA, you can take the FPGA bit stream, you can take the ELF file that the software creates, and you can merge that ELF file into the bit stream, into the FPGA bit stream, such that when you configure the FPGA gets configured, the processor gets instantiated, and then it starts running your application. So
basically, your code from the microcontroller is some kind of built in the firmware of the FPGA.
It gets built into the firmware of the FPGA, and it just starts running. If you want, however, if you want your application to run from DDR because it's a bigger application, you can't do that.
You have to load it somehow.
So you have to create a bootloader, and Xilinx will give you that bootloader that merges into the block RAM file, and it's the bootloader that merges into the block RAM files, such that when the processor starts running, it can go off to like a QSPI memory and pick up the software application that you've got and then move it into the DDR memory. And that makes it a little bit more complicated. We're not really going to go through that today, but if anyone's interested, I did just put some links with a detailed step-by-step PowerPoint on how to do that on my website, just because I realized I'd written how to do it long ago and I'd not shared it. So it's been on there. So we've got this DDR3 controller now. It's got the DDR pins connected. It's connected. It knows where the DDR pins are. We're going to double click on this to configure it a little bit. And just so as I can show you what's inside it. It starts out showing the Xilinx Spartan 7, the device that we're targeting. We're creating a design, for example. We only want one controller in it. And I'm not too worried about making any pin compatibilities. I'm not worried about, if you want to make it compatible, then you can select this option here, which will make
What does
sure
it mean, pin
compatible?
compatible?
So if you have different size FPGAs,
okay,
it will make sure that pin that can migrate. So if you see here, while we're designing for the S50, we could also tick this box for the S25, and what it would do, it would make sure that any of our configurations here are valid on both settings.
So you can kind of use both chips on same board.
You can use the same. Yeah, you could use the same. You've got a migration path if you wanted to on the same board. Yeah, or the same design across those boards. So we'll click on next on this. We're going to target DDR3 because that's it's on there. And the nice thing about this is all configured and set. So we don't need to make any changes or anything to this. So we can see the clock period that we know it's going to work from, the time. It's got the component there. It's got the voltage, the data.
This is all specified in the XML file.
This is all specified in the XML file that defines the board. So once we've got that, we're going to click on next. We're going to leave everything. So this is the width of the width of the data that goes into it. So even though the data bus is only 16-bit wide, we want to get the highest performance, the highest throughput we possibly can. So we're writing into this and buffering in 128 words at 128 bits at a time into this controller. So I'll show you that in a second. So, and then there's some buffers internally to handle that.
So axis data width is the bus between the microcontroller and
between the microcontroller and the memory controller.
Mm-hmm.
Yeah. So we're going to click on next for that. Now, what we're going to change here is we're going to change this input clock frequency, and we're going to change this to 200, which is what we've just set our clock frequency to be at.
Mm-hmm.
There's additional clocks that are generated that are coming out, if you notice. So so everything we're going to do now, we're going to make sure that the clocks are synchronous, that all the clocks are generated from this memory interface controller that we run in our system, so the entire design is synchronous. So if we want to, because it's got PLLs and MMCMs in there, we can have additional clocks coming out of it, just like we did in the clocking wizard earlier on, where we say, oh, we want to clock at this frequency, clock at that frequency. We're going to leave it unchanged. We're not going to use any of those. What we're going to do is on the next tab, we're going to tell it that the system clock isn't coming externally, it's coming internally. We're going to give it from somewhere in the logic. And then we're going to allow this one here. So the XADC. So the XADC it's an ADC that's actually in the FPGA component itself. It gives us the visibility of temperature and voltage rails that are supplied to the FPGA, and up to 17 external signals. So you can use it to monitor external signals if you want. The memory controller uses the XADC to get the temperature of the device such that it can compensate.
I didn't know you can do this. That's interesting.
We could do another session. We could do another session if you want on that XADC. You could fill an entire hour with what you can do with sort of that little ADC in the FPGA. It's really quite interesting.
Because I remember when we were designing boards with DDR3 memories, we had to run the test in very low temperatures and high temperatures and hope that the settings will work for whole range. But here you can actually adjust the timings based on the temperature. Oh, that's cool.
Yeah, so and by instantiating that, so you get two options. Obviously, there's only one XADC in the FPGA. If you instantiate it within the sort of the memory controller, you can't use it for anything else. If you don't instantiate it within the memory controller, you can use it for whatever you want, and then you can ask it to give you a temperature bus that you connect to the memory controller. We're not gonna instantiate one on our own. We're just going to say that we're just going to enable it, and then we're going to leave the on-chip termination as it is. We're going to leave the pinout as it is. It's going to come here. It's going to give us the pinout because the pinout's already defined in this XML file. We're going to click validate, and we should see that it's all good. By the way, if you're designing your own custom Xilinx board that's got DDR memory on it, you should run through this before you actually build the board, just to make sure that it all works and it's all valid. So once we've got that, we're going to click on next, and we're going to click on next, and we're going to click on the final one. We're going to accept the license and next, and then it's going to generate. It's just going to update that program there with the changes that we made.
So basically, you can run this without connecting the board, so you are sure when you do your pinout and connections in schematic, you can actually really create design for that schematic.
Yeah, and you can be sure that it's a valid pinout, because I've seen some of my clients have come to me and said the DDR doesn't work, and it's like, yeah, unfortunately it doesn't work because you've not got the pinout correct.
And then you have to redesign the board.
And then you have to respin the board, unfortunately. Yeah, so that's always expensive. So there's a couple of it always puts a couple of pins in when it does it for the system clock and the reference clock. We're going to delete those, and we're going to connect the clock out to both of these. So both of these are getting the 200 megahertz clock. What we're going to do then is we're going to add in our MicroBlaze. So we're going to click on this little add button. We're going to type in MicroBlaze.
So this is the microcontroller core.
So this is the microcontroller. We're going to double click on the microcontroller IP. actually make that a little bit better. So there. In fact, actually, I could pop this out so as it makes it a little bit bigger, and then do that. So this is our microcontroller IP here. We've got our memory controller, we've got our clock. What we're going to do is we're going to run this thing here called block automation. And then this allows us to configure the microcontroller at a high level. It gives you a very granular, shall we say, not a fine grain, but a very granular configuration of your processor. You might want to come in later on and make some more changes, but at the top level, it'll help you change it. So the first thing, how much block RAM do we want to make? Do we want to provide it to use to run its applications from? I always tend to give it by default sort of 32 kilobytes. I don't want any ECC. I'm not going to bother putting any ECC on the memory. It's going to run on my desk. That should be okay. The cache, do we want to have any cache memory on there? So this is to provide this is to increase the performance. If we're running from DDR, then we can increase the performance by having cache memory and again by using block RAMs to act as caches, such that it can speed up a little bit faster.
So the cache will be the SRAM memory in the FPGA.
In the FPGA, yeah. You don't want to put the cache in the DDR memory. You want it to be it's additional block RAMs that you're using in your
and local memory. That one will be in the DDR memory.
No. The local memory will be in the block RAMs as well.
Okay.
So the difference being, you could run your application from the local memory, and the processor can see the local memory.
Oh, so the local memory will be used for the bootloader.
For the bootloader or for anything like that, or a small application if you've got it. The sort of the cache sort of pretends to sit on top of the DDR, doesn't it? So it just goes to the cache and gets a cache hit or not.
I understand. So the local memory is the memory which can be programmed with the FPGA code directly.
Yeah.
Okay.
Yes, we can program that directly, and we can do the same. Excuse me. We can do the same with the DDR as well. We can target that. We're gonna select the clock. We're going to tell you that actually we want to use the output clock from the DDR controller. So we're going to be all nice.
So this is the clock for the microcontroller.
The clock for the microcontroller.
So it's going to be clocked by 81 megahertz.
81 megahertz, which is one quarter of the frequency that the DDR is running at. So the DDR is running at 4 times 81 megahertz.
So when we selected 200, how it can run?
That is the 200 is the input clock frequency into the DDR controller. Again, there's a PLL in there that's creating the clock.
Okay.
That's creating.
So the bus itself is going to run on a little bit different speed.
Yeah, so the bus itself is going to run at a quarter of that, which is 81. So we're going to click OK on that, and it's going to take a second or two to run through.
I can't imagine how long it would take me to discover how to do this if I would have to do it by myself.
It's relatively simple to step through and work through. And there's some good tutorials. So what do we have here? Now? So you'll notice it's gone through. It's connected up. We've got this block here, which is called the processor reset block, and literally all that's doing is it's taking in the resets from the memory interface generator and from this module over here, which we'll talk about in a minute. And it's essentially synchronizing them to the clock that the processor is running at. So it's synchronizing the signals and the resets.
And this was automatically created when we...
This was automatically created when we said run the block automation. We have this block up here, which is the debug module, essentially. So this is essentially provides the JTAG connection for us.
That's the point which you can connect the logic analyzer?
No, not yet. So we're not connected to the logic analyzer. This is literally just to give the processor so this allows us to talk to the microcontroller, and stop and start and download new instructions and halt and breakpoint and all those things.
So there is like
So
a connector for this block, like JTAG connector?
Yeah, so yeah, it just connects to the JTAG. It's actually hidden, you don't see it in here, but the JTAG connector on the board actually connects to this connector here.
Okay.
So we have this debug interface, and then over here we have the local memory interface. Now the MicroBlaze it's a Harvard architecture, so it has instruction and data buses. And in this local memory bus, what it essentially has done is it has this local memory bus controller essentially, and then a BRAM controller, and then essentially a BRAM block that's in the FPGA that's set. And this is where you could run your applications from if you want to, or you could run it from, as we're going to do. You could run it from the DDR, provided you connect it all up properly. So what we're going to do, we're going to double click on the MicroBlaze even. You can see if we want to, we can have a 64-bit processor, but we're going to run it as a 32-bit. We're going to leave everything else pretty much unchanged. We don't want to implement any of the fault tolerance or the optimization.
So basically, I'm going to interrupt you for a moment. So basically, we configured the microcontroller when we were inserting the block, but then we have to go back and we have to configure it again.
Yeah, there are some. Yeah, so as I said, that initial block automation, it's a very granular sort of. Yes, you want this type of processor created. Then we can perhaps take a step. Then you can re-customize it and say, actually, I want to include this interface, that interface. I want to do this, and I want to do that. Okay. So you can change it a little bit. And if you've made any changes to your ARChy, because obviously engineers never make any changes to their system, do they? Nothing of it. So if you've made any changes that require a different type of configuration of the processor, you can do that. So what we're going to do, the only reason I wanted to re-customize this was to enable this interface here, so that we have both instruction and data interfaces that are on the AXI.
Why we would like to have it?
This is so as I can talk to the DDR memory. So this is how I'm going to be able to run my application from the DDR memory, is by connecting the AXI instruction and the AXI data instructions from the processor to the DDR memory, such that it can access it. So that essentially the DDR memory is going to appear in the memory space of the in the memory space of the MicroBlaze.
This would be a tricky one, because you have to enable it, otherwise something is not going to work, and it is only one checkbox.
So once we have these, so you can see these two ports here, and we can see we have this port here for the.
Okay, I understand now.
We want to connect the two together.
Okay.
But obviously AXI is a point-to-point interface. It's not multi-drop. So we need to put some sort of bus switch in there essentially. And so what we're going to do is we're going to run this connection automation now. We'll connect the reset. We'll allow it to connect the resets up now as well. Actually, I'll do that slightly differently in a second. What we'll do is we'll connect the AXI up.
Okay, I will stop you now. I will stop you now. So here we are going to select what we would like to connect, correct?
Yes.
So we would like to connect these AXY interfaces or something. Connections.
Yes.
Okay.
Yeah.
And if you select all of them, then it will connect everything, or we are going to connect the reset in the next step, or why you didn't select?
If we select, just because I wanted to make sure that I connect the resets properly in this system, because one of the pitfalls I often find when I build these MicroBlaze systems is I manage to hold the processor in reset by putting an active high reset into an active low or something like that, and then I progress through. So I'm going to connect this. What it's going to do is it's going to run through. It's going to put us in what they call a smart AXI interconnect. So I'm going to click on OK. And there we go. It's connected. It's put this smart interconnect in, and you can see the slave ports coming out of here, the master ports running back round here, and back into there. What I'm going to do though is I'm going to double click on this, and I'm going to change the number of slave interfaces to 2.
Because you would like to, okay.
And then I'm going to do that. Then I'm going to do that and connect that. For these locked, for the reset into here, for the system reset here, what I'm going to do is I'm going to connect that system reset to the locked signal. So it's an active low. So while the clock is not locked, it will sit low, which will hold the DDR controller in reset, which will hold everything else in reset. Once the PLL locks, it will come out of reset. It will deassert the reset on the memory block, and then that should ripple through, and the reset should clear through quite nicely. What I'm going to do, I'm just going to pop this back in for a second and hit this block, and so you can see it. I'm then going to drag in the system reset. And if you can see, it wants to go to this block here, so I'm going to connect that.
Oh, it's telling you where it would like to go. Okay.
Yeah, it's quite smart. If I double click on this reset, it's going to tell me that it's active low. That's the board reset is active low. If I double click on the clock wizard, I just want to double check that because I'm pretty sure it thinks the reset type is active high. So I'm going to change that to active low. And then I'm going to click on OK. And then I'll just have to connect that again.
And this reset pin, that's the pin on the FPGA?
Yeah, that's one of the pins on the board. So it's this little button up in the top of the FPGA.
And it's connected to the FPGA?
Yeah, it's connected directly into a pin on the FPGA.
And this kind of port, what we can see in the schematic, that's basically the pin where the reset button is connected.
Yeah. Okay. So we're going to talk through that. We're going to talk through that in a little while because they're called constraints. Okay. And we're going to talk through that in a second.
So these gray arrows, these are representing physical pins.
These are physical pins on the FPGA, physical input and output pins on the FPGA. Now, we've got here a lovely little MicroBlaze system. Now we've got a MicroBlaze that can run from memory. We can debug it. We can stop it. We can't say hello world yet though, because there's nothing talking to the UART. So what we're going to do is I'm going to pop that back in. I'm going to scroll down here. I'm going to see this USB UART down the bottom of the board. I'm going to pick this up. I'm going to drop this on the board. And it's going to add me, and I'll pop that out just so we can see it a little bit better. It's going to, where's that gone? Oh, put it down there. It's going to add me this AXI UART. And you can see it's connected to the pins on the board that will connect to this little pin here. And if we double click on it, this is just a standard UART. We can set the data rate. Let's set it to a sensible, 115200, no parity, 8 data bits is fine. We'll click on OK. And then if we run this connection automation here, what it's going to do is this AXI interface here, it's going to connect it into our MicroBlaze system. So we're going to click OK. And there we go. It runs. It's now connected to this interconnect. We can see it. We can see it there.
Okay. And this UART output is connected through some UART to USB converter on the board.
Yeah, it's connected to a little UART to USB connector, so we can see it. We can see it. We can see it in a terminal when we run it.
Okay.
So this really is the completion of our MicroBlaze.
I'm really curious if it's going to work.
Yeah, that makes two of us, because live demos always never quite work, do they? But the thing that we've not quite done is we've not addressed all of the. We just need to check that the memory looks good for the data, and we just need to assign. We'll do assign all. Because what we really want to see is that both the data paths and the memory and the instruction path, they've got valid paths to the data. So you can see here we've got the local memory that starts at address 0. We've got the DDR memory, which is 256 megabytes, and then we've got the AXI peripheral like this one. So Xilinx rather nicely, helpfully gives us this lovely diagram here, which shows us where things sit in the address space. So so if you build it and something looks like it's overlapping or something like that, then it's not a good, it's not a great thing to use. Now the next thing that we wanted to do, is we want to create a little RTL module that gives us this control over the switches and everything.
Okay, what
like
RTL? Okay,
VHDL,
I guess we will
VHDL,
see. Okay.
VHDL or Verilog. So hopefully I'm going to open my editor here, which is, there's an editor built into Vivado, but I tend to prefer using this VS Code editor, and it has an add-in called Teros HDL, which is really quite nice.
So this is the code which is pure FPGA code. This is the one which is going to live separated from our microcontroller. So
this is the FPGA code. This is going to separate to our microcontroller. And if you're not too familiar with it, I'll give you a quick talk through. I've got the IEEE library in there twice. I only got in there once. But what we have is we have the initial setting up of the library. So the calling the standard like you do in C or C++ when you include standard lib.h or whatever. We've got the entity. Now the entity, essentially, if you think about it as a component, an electronic component, the entity defines the pins. So the physical inputs and outputs of this block. So we have a clock input, we have an enable input.
So this is going to create the block which we will see in our diagram?
Yeah, in our diagram, yeah. So we have an enable input, which will come from one of these switches. We have the switch in, which will come from the other three switches. We have an LED enable. So there's a lot of single color LEDs on here as well. So we're going to turn on one of those LEDs when it's enabled. And then we're going to have the actual RGB LED, which requires 3 bits. We've got the output. We've got the output here. We've got a very simple state machine then. So we've got the architecture. So if the entity defines the pins that are coming into the module, the pins that are coming into the module, the architecture defines the functionality, what happens inside that module. So we've got a very simple state machine, and you could do this without a state machine. I just think it was easier for demonstration purposes to show that a state machine was there. So we've defined the states that we want our state machine to have, so idle and enable. And then we've defined a signal called current state, which can take on the states of these two state machines. And because it's an SRAM based FPGA, you can do this. I've actually said that it's, the default state for this is the idle state. And then we have a little process here. So this process, every time the clock occurs, so every time a clock transition occurs, this process will be executed, and it will run sequentially from top to bottom. So first thing it's going to check, is it a rising edge of the clock? So we're only going to do any actions on the rising edge of the clock. And if it is the rising edge of the clock, we're going to run our state machine. So we're going to say, well, when we're in the idle state, we want the enable LED to be the LED that shows that we're currently enabled to be turned off because we're not currently enabled. We want the LEDs going to the tricolor LED to be turned off because we don't want any colors coming out of them. And then we just wait. And we wait forever and a day for somebody to flick this switch to a 1, to a logic high. If it goes high, we jump into the next state. And in the next state, we turn on the LED to show that we're enabled. And all we do is we pass through, it's really complicated engineering this, we pass through the state of these 3 switches to the LED.
Okay.
And we don't do any switch debouncing or anything like that because it's never actually going to make it into the field. It's just for teaching and demonstration purposes.
Okay, I understand.
And then we say what happens is if the switch goes low, so if the switch goes to inactive, then we go back to the idle state and we turn everything off again.
Okay.
Really simple, really nice thing. If you want to visualize that, this is why I like the Teros HDL editor. And it is an open source editor, it's really good. But if you've got it installed, you can click on this module documentation. And in the best interests of modern demonstrations, it doesn't run. it runs through and it generates you a lot of documentation. So it generates you a little diagram, little block that shows what your block's going to look like. It shows you the ports, the vectors, the signals, the types, and then it even draws you the state machine.
Okay.
So as you can see that the state machine is how you'd expect it. In this case, it's really simple, but when you're developing that RTL, you can run through and see that that's what you would expect your state machine to look like.
Okay, so we have basically created our own module, and now we have to use it.
We have
block
created
diagram.
our own module, and we're going to use it in our block diagram. So the first thing we're going to do is we're going to come back into Vivado, and we're going to click on the design sources, because we need to add this as a design source. So we're going to say that we want to create or add design sources. And we're going to click on next, and then we're going to click on add files. And we're going to go navigate to the area where I saved it. I saved it actually under my dry run through of this. So yesterday I did a dry run through. So I saved it under the LED. So I saved it as LED FSM. If you want to, you can say copy the source file into the project. So I'm gonna leave it in the space it is, and then I'm gonna click finish. And what we see is our VHDL module popping through here. Now I'm going to create a wrapper, a HDL wrapper for this design. And the reason I'm going to do that now, and I'm going to let Vivado manage it. So Vivado is going to create me a VHDL or Verilog, I can't remember which one it's set to by default. It's going to create me a VHDL description of this.
So now it's creating the block, which we can then use there.
Oh, well, no, this is creating the overall block, the overall description of this, of what you can see in this diagram window here.
Of everything.
Of everything. And I'm asking it to do that. And hopefully it is, it's updated. I'm asking it to do that because I actually want to set that. When I loaded my little LED block, this little symbol here tells Vivado that that's the top level of the design. And it's not, it's just a little component in the design.
I understand.
But you can't add this to the block diagram if it thinks it's the highest level.
Okay, I understand. We would have to.
So I've created this wrapper here, which describes this block diagram. And then I can take this one here. We can right click on it and we can say add module to block design. And there we go. It adds it
I understand.
to the block design. What we're going to do now is we can just connect it up. So I don't really want to run this off a 200 megahertz clock. It's a little fast. So I'm going to run this off the 12 megahertz clock that's coming in. And then what I'm going to do is I'm going to select each one of the outputs here. Each one of the inputs and outputs. And I'm just going to tell Vivado that I want to make them, that these go external to the FPGA. So it's going to put some...
They are connected to pins.
It's going to put some pins on it for me. I'm going to rejiggle my design a little bit. I'll pop it out. And then you can see, so we've got this microprocessor section here up the top. And we've got our little FPGA design element here down the bottom. And these are the inputs.
We still need to connect
outputs.
them to the switches and LEDs, I guess.
Good. Yes, we do. So what we're going to do, so there's two ways to do that. I'm going to just save this design now.
Okay.
And then I'm going to verify the design to make sure that I've not done anything silly. Hopefully I've not. So Vivado's going to take a few minutes to run through it all, and hopefully it should come back and say, yeah, there's no errors. So we're good. Let's save it again now.
You press play, yeah, now.
Then what I'm going to do, well, I'm only going to press it once because I don't want it to run fully through. So I'm going to ask it to just do the synthesis for me.
Synthesis, what does it mean?
That's a great question. So all these blocks, even the blocks I wrote, the blocks at Xilinx IP, they're described in a hardware description language. So they're described in VHDL or Verilog or System Verilog. What synthesis does is synthesis takes that register transfer level description, and what you're describing in your design is how data moves between registers essentially. So state machines, counters, mathematical operations. synthesis takes that operation, and it creates from them the logic equations that you would need to implement that functionality.
Okay, I have a question. Why we didn't assign the pins to the switches and LEDs and we run this synthesis? Do we need to run it again then?
So the synthesis is actually creating the wrappers, the logic. It's not actually done any assignment to the external world. And the reason why I've done the synthesis first is there's two ways to write the constraints that do there's two ways to create the constraints that you use to do the pinout. The first way is you can write a text file called an XDC file, and you write in there and you say sort of set property, this pin, this signal is at this pin. Or the alternative option is you can open the synthesized design like we're about to do now, and you can do this from like essentially from a menu.
And I guess it's better to run the synthesis first because it's focusing on the design implementation, and where exactly the pins are you don't care. But if you define the pins first, maybe it can try to do implementation closer to the pins, or no?
Well, the synthesis is not aware of the physical location of the pins. So the
okay, you just explained. I understand.
It's just creating the net list.
Okay, it's not the placement yet.
No, the only reason I did it first, really, if I'm brutally honest, is because this video is a bit of a tutorial, and I figured that most people might not be familiar with how to write the constraints file language.
Okay.
But if I showed them how to do it via this graphical method, it creates the file for you, and it makes it a little bit easy. It makes it a little bit easier for them. What I've got to do, obviously, in the normal world, in doing this, in the normal world, you would look at the schematics of the design to work out what things are on what pins. I actually know this from the walkthrough. I actually worked this out yesterday and did the walkthrough. So I'm just gonna cheat in the interest of time and look up the pin numbers. But what you can see in our design here is, we've got the DDR pins. Mm-hmm. They're all in. They've got the right DDR IO terminations and IO standards. But we have some. Mm-hmm. For instance, these pins down the bottom that don't have any package.
So all these red ones, we need to fix this.
We need to fix and tell them where they are. Mm-hmm. So they are all, with the exception of one, they are all LV CMOS 3v3 pins. So they're all CMOS 3v3.
Okay.
With the exception.
So this is the type of the output.
This is the type of the signal, so whether it's an LV CMOS 3v3. Mm-hmm. The only exception...
signal, yeah, because some of them are inputs.
Yeah, the only exception to this is this one here, switch input 2, which shares the same bank on the FPGA as the DDR. Mm-hmm. So its IO standard actually is SSTL, subseries terminated logic 1.35. And if we don't set that correctly, so if we said that there was 3v3, even though we know it's not, the tool will pick it up and give an error. And so you've got you're breaking the voltage rules on this bank. You can't do it. So now we know that we can actually give them some pin location. So I know this one, for example, is on G17. I know that I worked out the next one was on G.
So this is the RGB LED.
These are the, that's a good point. Yeah, so this is the RGB LED. So yeah, so that's on G17. That's a good point because I've actually set the wrong one there.
Yeah, that's why I was like, oh, they are all same
output. No, that's a good point. That's a good point on the LED. It's actually the switch that is. There's a way you have to be able to remember what you've named your signals and why accurate naming of signals is good. So we know that one was on G17. We know pin 1 is on G15. Mm-hmm. and we know LED 0 is on F15.
So based on schematic, you find which pin they
Yeah,
are
so
connected.
I just looked at the schematic design and worked out which pin the engineer had connected them to on the board. So we know that switch input pin 2 is on M5. We know that the next one is on QPT. We know that the next one is on DPT. Now I have to be careful here because I didn't mean to put that one on A9. I'll slide that in a second. I have to be careful because when I did this walkthrough yesterday, I got these two the wrong way round, and it caused me literally ages to work out which way round they were. So enable is H40, and this one is E80. So we've now assigned all of the pins that we we want to.
And the scalar port enable input, that's again one of the switches.
The input, yeah. So this is the enable is so these 4 switches. So one switch gives the overall enable to allow the other ones to actually work. It's a bit of a contrived example, but
okay,
and then
I understand.
This one's H80.
Just double check if everything is okay, so it works.
Yeah, I'm just double checking. I think we're good. What we'll do is we'll then save this, and it will ask us to save the constraints file, and this would be the one that we could handwrite. So we're going to click, but we don't. So we don't have one. So I'm just going to call this IO. I'm going to click on save, and then under my constraints file, I now have a new constraints file.
This is what you could write manually.
This is what you could write manually if you knew how to do it. But because I figured people watching this video might not know how to do it, then this is the way
good.
to.
That's much better way.
This is the way. This is the way you can. This is the way you can.
Yeah, I like the graphical way and you know all the pins, and I like it.
So what I'm going to do now is I'm going to close that synthesized design. And I've just remembered actually what we forgot to do one thing in this design. So we forgot to add in integrated logic analyzer. So we're going to double click on this.
So we have to run the synthesis again?
Well, yes, but it's not as bad as you think, because how Vivado does the synthesis is it synthesizes each block on its own, and then it creates the top level. Then it does the top level synthesis for the overall design. So if you only change a block, the only thing that changes when it just redoes the synthesis for that block, and then the top level, then the top level of the design. So it shouldn't take too long to redo it all.
Okay, and analyzer analyzer block. That's what we are going to use to see what is happening inside of our FPGA.
Yeah. So we're going to see what's happening inside of our FPGA. We need a native. We just want logic signals coming into it. We'll store 1,024 samples. That's more than enough. But the number of probes we want is 1, 2, 3. We want 4 probes. Can't type. 4 probes. And then the probes we want 1-bit width, and we want 3-bit width, 1-bit width, and 3-bit widths. So what this will do is, if you can see, let me pop this out so we can see it a little bit better. So what we do is we've got this ILA here, this logic analyzer. We're going to connect the clock. This is the sample clock. So we're going to connect that to the same clock that the FSM is connected to, so it's sampling at the same frequency. We're going to connect this probe 0 to the enable switch. We're going to connect the next 3 ones to the switches, so as we've got a vector, so as we can see the switches. We're going to connect this one to the LED enable output, and then we're going to connect this one to the final one.
Theoretically, you could also connect this block together with the microcontroller.
So yeah, I mean, these ILAs, they're really fantastic. They really help you to do some great debugging in the FPGA, because simulation is good, but sometimes sometimes it's the interaction in the FPGA that causes you the issues. So yeah, you could if you wanted to,
I mean,
you
you could connect our LED state machine to the microcontroller to see, for example.
Oh yes, we could connect that if we wanted to. We could connect that to a. We could
How would
connect
you
this
do
to a
that?
GPU.
I'm just curious. So you would add some kind of.
So we would add a GPIO block.
Oh, so you can add GPIO to the micro. Oh, cool.
To the micro, and then we could say then we could connect. In fact, I didn't try this in the walkthrough demo example, but because it's Friday and I've had a productive week,
we are going to do it.
We're going to do it. So we're going to connect it into the. So it's now connected. You can see the GPIO is connected into the processor memory space here. And I'm just going to double click on it. What we're going to do is I'm going to say this module is all inputs, and I'm going to give it. Let's look at the 3 and 3. So because there's 2 ports, it can do dual channel. I'm going to configure them, but both of these channels to be inputs, each of which is 3. Actually, no, that's wrong. Yeah, each of which is 3 bits. Then I'm going to click on OK. If I expand that one, what I'm going to do is I'm just going to connect this one to this point here, and this one to this point here. So we can see now our FPGA. Let's just tidy up the diagram a little bit if it wants to. So our processor now can see the status of what the switches are coming in,
cool,
and what the switches are going out. Let's just go back to the address editor, and you'll see that it's connected in automatically, the GPIO. So if we look at the address map, the GPIO's appeared there, and it all looks good. Now you have to remember this address that it's put it in at, because I didn't write any.
That's the address where we will read the.
Yeah, I didn't write any software for this. So how we're going to prove this works is we're just going to look directly. We're actually going to debug it and look directly in the memory.
Okay, perfect.
And such that we can see things changing.
Okay.
If it all works. So now let's save that. And this time now we're going to generate a bit stream.
If this is going to work, then. For how long I have been putting away these FPGA boards which I have, because I was like, it's super complicated to start with it and I don't really have time to. If you will be able to do this in 2 hours, then I will be like, wow, I have to switch on one of my boards what I have there.
So you have the ARTIX version of this, you were saying, don't you?
I think
so. Yeah. You could everything we've done today. You can do in the ARTIX. You just pick the different board at the beginning. You just pick the ARTIX board at the beginning, not the Spartan S7.
I will.
So this is gonna run through and create our design. So so if we say that the bit stream's run, it's taking its time to complete. We can open the implemented design.
So now it is.
And now we're going to see where. Now it's finished. So now we're going to see where everything is in the FPGA.
And blue is used.
Blue is used. Yeah, blue is used. It looks
almost a lot everything.
Oh well, it looks like that. Let's just let it finish. It has a way of making it look like it's used everything, but it's actually not. So if we go to the project summary,
okay,
then we'll see that actually in terms of lookup tables, flip-flops, we're below 50% utilization. It's just because if you zoom in, it's where it's placed them, it's where it's placed them, it looks like it's used. It looks like it's used everything. So we'll run that report. We'll run that report, the design analysis report. I'll ask it for the complexity, and we'll click on OK. And it'll take a few seconds to run through. In the meantime, I'm going to plug this board into my PC. Look, we've even got a red light on it, so it's got some power.
You only need to connect USB, or there is also power supply?
No, it's powered over USB.
Okay.
It's powered over USB, which is good. So we can take a look. We get the general information. We can see the setup, and we can see the timing and the setup information here. So we can see that most of it doesn't look too bad, actually. It's
I have no idea. How do you know it doesn't look bad?
So I can tell you that it's not looking bad, because the actual timing summary here is saying there is zero failing endpoints for setup, 0 failing endpoints for hold, and 0 failing endpoints.
That's what we should be aiming for, yeah?
That's what we should be aiming for. So when you do the design analysis report, all these paths actually time. Their timing is good. If they're bad, you'll see reds and negatives and such like. If we look at the complexity, now you can pull this up when you've done synthesis. So before you go and spend hours doing place and route on a complex design, you could pull this up and you can take a look at it. And you can take, there's a couple of things here with this rent analysis and the average fan out. And you can see that if a good rule of thumb is that if the rent figure here, the rent exponent here, is below 0.65 and the fan out is below 4, then the design is considered by the tool low risk. And it doesn't think that implementation is going to be an issue.
How did you come up with these numbers?
These numbers are what Xilinx tell you in their documentation. If it's between 0.65 and 0.85 and the fan out is between sort of 4 and 5, then it's considered a more complex design, a highly complex design, and you might have a little bit more issues trying to make it achieve timing. And if it's above 0.85 and the fan out's above 5, then good luck. You're gonna have some fun with it. By a little rule of thumb that we have as a company is that we try not to fill the FPGA more than on the first initial design for the customer. We try to make sure that it's no more than 60%.
Okay.
And that gives us on the prototype, that might mean that you've got a slightly larger part than what you actually want. But it means that you can be guaranteed that you're going to find a way to get the design working and get the timing. And then you can do that. Then you can do that design space exploration to try and say, well, what smaller part can I fit? What smaller part can I fit it in, and take it from there. And yeah, so it's going to give you. This is going to give you some nice. The design analysis. It's going to give you some nice analysis on your tool, on your design, and tell you whether it's hopefully going to work or not.
Okay.
But like I say, our design implemented really nicely. So let's go and see if we've got the double. Not only have we got no timing issues, no timing errors, let's see if it actually works, which will be just as challenging. So what we're going to do now, the bitstream's been written.
What does it mean, bitstream?
So this is the configuration file that we download into the FPGA. So this is the configuration file.
Okay.
Of the FPGA.
So that's like the firmware or the code, or binary.
It's the binary, I guess.
Okay.
It would be. It's the binary. So what we're going to do is we're going to go to File in Vivado. We're going to go to Export. We're going to export our hardware design. We're going to tell it that you can, if you want to do this, if you're doing a complex design, you can export this pre-synthesis, so without any bit streams or anything. And then the software team know what IP you've got, know what memory locations things are at, and they can start writing their software.
That's what we did in the previous video.
In the previous video, because we didn't have a bit stream. So this time we're going to do with a bit stream. We're going to hit on next. I'm going to leave everything in the default locations as just to where it is. And then we're going to click on finish. And then that will have exported the XSA. So then we're going to open VITIS, which is the software development environment.
So basically now we finished our FPGA code.
We hope. If we got it right, we hope. So now we're going to open VITIS. We'll know literally in the next 2 minutes or so.
And now we are going to write the code for our microcontroller.
Yes, yeah. I'm going to connect it to my serial port, COM port 32. And I'm just going to change the serial port setup to 115.
You really have...
I'm just going to move that off screen for a moment.
Do you really have like COM 32?
Yeah, I have a lot of boards that connect. It goes off the ID of the USB ID chip, so it just throws them. It just throws them in. It's actually quite frustrating. So I'm going to go to the project area that we've got on that was created by Vivado when it created it, and I'm just going to create a workspace folder. And this is where we're going to let VITIS to open. So that inside that workspace folder is where VITIS is going to run, and it's going to keep all the software.
I'm really curious.
Makes two of us. If this works, I think I've earned a beer this evening. So once VITIS opens, what we're going to do is we're going to click on this Create Application Project. Not really much. This is just a little information tab that tells you the logic of how it all works. We're going to click on Next, and then we're going to actually pick the hardware that we've just exported. So we're going to go to Browse here. We're going to find the hardware that we've just exported. So there it is. It's the XSA. It's today's date and time. That's obviously the UK time. We're going to click on OK. It'll take a second or two for it to be pulled in. There we go. So we're going to use this one. We're going to give it a project name. So we'll call it Hello World, I guess. So we'll call it Hello World. Then the next tab's going to ask us what domain do we want to create and what processor do we want. We're using a MicroBlaze. We don't have any operating system for it. We're just going to use a standalone bare metal. It's a 32-bit MicroBlaze, and we're going to click on Next. And then it's going to give us a template as to what we want. So this template, let's not push it. Let's just say Hello World.
Okay.
So we're going to say Hello World here. So this is going to run through, and it's going to create as our project. So what we're going to find here is the first bit here is what's called the platform. And under the platform's got all the drivers that we might need for the design. So if we look under the board support package, we've got under the library source, we've got the drivers for the CPU, the GPU, the MIG, the UART. All the drivers are all there to allow the tool to work. It's got all the include files that are needed. And everything. It's got the hardware elements, and it's got the platform. If you wanted to export this platform, it's got all that. We've also then got the application, so we can have multiple applications. So you can, on the same hardware platform, you could create multiple applications of software to run at different points in time if you wanted. So we've got this one hardware. On our case, we've got this Hello World system. We've got a little bit of C here. And it's going to literally print Hello World and successfully run the application. Let's change this a little bit to Robert and Adam say hello, just to make sure, just to prove to people that we are actually doing this, to say that we are actually doing this in real time. So we've got that. We've also got a linker script. So the linker script by default tells it where you want to run your application from. So by default, if it's got DDR memory attached, it will pop it in the DDR memory.
I remember this.
Otherwise,
when I was programming very low level microcontroller, then this is all the mappings.
Otherwise, you can put it in the local. Otherwise, you can put it in that local memory, but we're going to leave it all in the DDR memory, and you can control the stack and the heap size and everything as well in there. So I'm going to close that. What I'm going to do is I'm going to click on this button here, the top level. I'm going to click on this hammer, which is going to build it, and hopefully I've not made any changes apart from one line, so it's going to compile.
Show the terminal.
I'm going to put the terminal up. Oh, it's not going to download it yet. It's not going to download.
Okay.
So what we're going to do then is, now we've got this, we've got the board connected, and I'm going to hold this board up for a second. And you should see a little, as we program it, you should see a little LED over here.
Okay.
And that means, so what I'm going to do is I'm going to expand this one, drop down. I'm going to go to the debug here. And I'm going to ask it to debug and launch it on the hardware application.
Okay.
So what this is going to do is it's going to download the FPGA file into the FPGA. Once that's configured, it's then going to download the software application into the processor that's running. It's then going to stop, or it better do anyway. It's then going to stop and wait for us to tell it to run, so that we can then tell it to run. So it's going to stop, it's going to run, it's going to download. See the FPGA download, see the little green light come on up in the top corner there. And you see the FPGA now.
Platform, yeah?
It stops on init platform. So this is the point. I'm going to pull my terminal window across here. I'm going to make this window a little smaller so that they can both be sat sort of next to each other as we step through it.
And move the terminal a little bit lower, because there will be cameras in the top right corner. I have cameras.
Okay, so if I move it down here.
Yeah, that's better.
Okay, so we've got the terminal, we've got the application, it's stopped. Now, we could click on run the application, or we could just single step through it. If you want, like single step through it, so single step through it. Oh yeah. Look at that! It actually worked. So maybe I know what I'm doing after all. So that's so that comes up, that says hello. We run the next line, successful printed hello, and then the program's going to die. So, but let's take a look at something else in there. So this is the debug view of the application, and right now the process has halted. So if I want to, I'm going to just make this. I can come into this memory monitor. We can click on this plus button here, and say I'm curious about what's in the DDR memory. So I can type in the address here, 0x8.123.1.2.1.2.
You could have a look where the switches are.
That's exactly what we're going to do. So we're going to take a look. So we can see here that we've got the, this is the actual, you can see the actual application if you want. If you want to break it, you can change it. But let's take a look at what the switches are. And the switches, according to my notes, were at 4. Now, off the top of my head, I think it's this initial register. I think it's this register here that we're interested in. And then there may be one of the registers. Maybe it's this register for bank 2. I can't remember. So let's give it a try anyway.
So show on camera. You are moving the switch.
So I was going to try and move the. We might have to run the processor for it to update and do it. So,
yeah. Okay.
But I should show the logic anyway. So if I turn the switch.
Okay.
You'll see this. This is the enabling switch, and you'll see this light come on and off.
Okay. So our state machine is working okay.
So if I enable it, and then I tell it to turn on the blue one, or turn on the red one, or turn on the green one. Or if we want to do, we can do combinations and have it white, or we can change it.
Cool.
So that's what we can. So it should. So
you have to refresh it, I guess, somehow.
I think we do. So I'm going to set these to be such that we've at least got a color. I'm going to set we've at least got a color in there, and then we'll refresh it. So I'm going to let me remove that one from and I'll remove the DDR one just in case I break it and return that one on. Oh, and look at that this time. It's 2. And what's the code on the switch? It's 2. So that's the software. Now, obviously, if you wanted to pick this up in software, you would have to write. Can we use the driver? You showed me there are drivers for GPIOs. there are. So there are the drivers for the GPIO.
Can we just read
here.
input?
Let's see if I can remember how to do it off the top of my head.
Maybe
so,
X GPIO-C or H, yeah, H, yeah. What is that?
So the C, these are the drivers. So this one is, if we take a look at the GPIO.H, you can see that what this does is it defines a configuration status for it. It defines the actual GPIO, and then it defines the.
Is there status?
It's this one, discrete read and discrete write, that we would use.
Okay.
So.
Can we put it into loop?
Oh, you don't want much, do you? So let's do this. So hash include xgpio.h. So what we want to do is I need a few things from the code. The first thing I need is this xparameters.h file, control So this xparameters.h file contains all of the memory address, all of the systems in the processor. What I need to know is I need to know this, which is actually 0, but let's pretend it's let's pretend it's not. So I need to know that, and possibly the base address. So let's go in here. So we've got the xgpio.h. What we're going to do, let's debug it, and this should go. This should go.
It's
mad
okay.
now.
You can play with the switches. Play with the switches.
Play with the switches.
Yeah. So we just connected the FPGA block with the microcontroller.
Yep.
Okay, and now we would like to.
So we have the FPGA block connected to So the FPGA block could do things the microcontroller could do things if it wanted to, in that FPGA block, and we've got it obviously running our application now, after a little bit of manipulation, but it's all there, it's all running. What we've not done though, so we looked at the memory here, and we've looked at the switch here. What we could do is we could go back to Vivado, and we could open the hardware manager, and just to wrap up,
we are going to run the logic analyzer.
And we're going to take a look at the logic analyzer. Now, hopefully it's going to connect to our thing. It's going to find our device. So there we go. There is one little thing I need to just double check first though, and that is the connection speed. So one of the things is with the ILA, it needs to be sampling fast. The clock going to the ILA needs to be faster than the JTAG clock, than the JTAG. And by default, that's not the case because I set this to 12 meg. So I'm just going to slow down the JTAG clock quite a bit. And then we've got what we can see here is we can see the signals. We've got the enable, the switch, the FSM enable LED, and the LED. And I'm going to click immediate trigger, and you'll see that it shows that these two are, the enable is high, the LED is high, and then the values of the other ones are 0. But if we wanted to say, sort of put some triggering conditions in there, I'm going to turn the trigger off. I'm going to turn the enable off, and I'm going to put this enable here, and I'm going to say what I really want to know is trigger on the rising edge, and then I'm going to arm the unit, and it's going to sit there waiting. So it's got a buffer of 1,024 samples to store the data in, and by default it gathers 512 first and then 512 after. You can change that if you want. I'll show you that in a second. If I come up and put this on camera, and you've got the screen on the camera, so if I do this switch here, we should see the ILA triggers on screen, and you see there the nice crisp transition.
So go back and change the other switches, and then enable again if the 0 will change to something else.
Well, we could change the switch if I want. I mean, we could trigger now. We've got that. If we just want to see the immediate value, the immediate, we just want to see the value that's on there. We can just trigger immediately, which ignores this condition here, and then we can, if we've done that, we should be able to see the values change into 3. And if I ask it to do auto retrigger, no, it's only going to auto trigger on the main one. But you can see it's running round and it's triggering as I change the values of the switch. And if you wanted to trigger on, say, if you've got a nasty bus or something and you wanted to see the value of that, you could set this up to trigger on. It's the switch in. So we could say in hex, if we say that value is 2 in hex, or we can arm it. Oops, sorry, that was me. We can arm it such that it's waiting, and I can come in here and I can change this value to 1. We might get some switch bounce because of some issues, but I'll change this value to 1. It's not triggered. Change this one to 8. Sorry, to 4. Not triggered. Still not triggered. I'll put this one back. We'll put this one on now, the 2. We'll put 2 on. Still not triggered because the value is not 2. Drop this one down. Oh, look, the value's 2. It's triggered.
Cool.
And you can see the previous value and the current value. And you can do some quite interesting things with it. This state machine, honestly. You can do some quite interesting things with this, like you can do with any logic analyzer. You can make it do state machine triggering, so it triggers in this state, triggers on this signal, then it waits for this signal, then that signal, then this signal. You can make it illuminate these LEDs when certain things happen. So if I'm doing a image processing algorithm, an application, when you've got a certain number of lines to come in, I set the trigger state machine up to count the lines coming in on the image to make sure I've got the right number of lines. And then it illuminates the LEDs if the lines are right or if they're not right or something. So it's a quick debugging thing that you can do. And you can change it to, you can change the window depth if you want, or you can change the trigger position. So if we change that trigger position, then it'll move down the beginning. It's all quite flexible. So
wow, within
2
hours.
What have we done? Within 2 hours, we've created a MicroBlaze system. While we've done a lot of talking, it worked first time. It actually worked first time, and nobody was more surprised than me. So we've shown that. We've then got it working with the, with the software. We've had the software running, saying hello world. We looked at the memory. We took a peek into the memory to look at the switch values in memory. You then lovingly challenged me to write some software on the fly to make it work, and we eventually got that working as well to give us that loop and throwing out data. And then we've got this final bit here, which is just the switches and getting it.
Adam, this was amazing. I think I will have to take out my Fpga Xilinx board and really try this.
So I want to see at the end of the video, I think it'd be really cool is if you could show your video, your little board doing the same thing. I'll email you. I'll email you the VHDL files. But actually, what I will do, joking aside, what I will do is I'll put all this on a GitHub so I'll put all these files on a GitHub so anybody wants to, and give you the link so anybody that wants to go and get it can.
Cool. You wanted to mention something about your book, or maybe even do some giveaways or something? I did. So I recently. So that's a good point. Well remembered. So I recently wrote a book on engineering, how to design embedded systems. What is inside of the book? Inside of the book.
So the book, well, the contents. So it tells you, really, it starts at the beginning. As you should always do on our system, with requirements. So it talks to you about how to create the requirements, from somebody saying, we'd like a board that can do this. So it talks about how to create the requirements, how to do things such as, engineering management, engineering governance, interface, working out interfaces, budgets, how to do the component selection for these boards. And
so is it about board design? Or?
It's predominantly, it's actually set into 3 elements. So the first element is on sort of hardware design. So it's talked about that requirements, that's component selection, and then the design of the board itself. So the design of the board was done in Altium, and it's available on, we've made the design actually available on open, whatever they call it, their open platform that shares it. Is it Altium 365 or something? Mm-hmm. So the board and everything's available on that. So it talks about the design of the board, how to do the schematics, the layout, the signal integrity analysis, power integrity analysis.
What is on the board?
So the board has a Zinc FPGA. So it has a Zinc FPGA DDR memory. It has a FLIR lepton camera. It has a vibration sensor, temperature sensor, accelerometers. It has Wi-Fi, Bluetooth, and Ethernet. And it has some remote sensors as well, remote temperature and remote humidity. So the board, the first half of it tells you how to design that board. The FPGA side of it tells you about how to design the FPGA elements that might go into that element. And then there's a final element, which is looking at how to calculate things like reliability for that board if you wanted it as a product, mm-hmm. and the things that you might consider as a system. So I'm quite proud of it. I think it's quite cool. And the boards work, which is even better. So we'll work out a little way to give one of those books away. I'm not sure how we can do that, but we will work out a way to give one away. Video.
We can what we sometimes do, we just pick up randomly from the comments from people who comments, or we can also choose the comment which you like, because you will be giving away the.
Yeah, and we'll randomly put everybody who comments his name in a little hat, and we'll draw a name. That'll be the fairest. Okay. That'll be the fairest way.
So are we going? Yeah. Okay. Go ahead.
I also have some S7s, so I will also give away one of these. If anybody wants to follow it through, I'll also give away a Spartan S7 board, and then they can follow it through and see how easy it is to do. And of course they can see how easy you found it when you walked through and did it as well.
Now I will have to do it.
Exactly. Now you have to do it.
Okay. Thank you so much, Adam. This was like super cool. I never really thought you can do so much in 2 hours. You can design your own microcontroller in 2 hours, and even with software which is running on it. Sometimes you buy microcontroller and it takes more than 2 hours to run Hello World.
To get up and running.
And that's everything for this video. I would like to say thank you very much to Adam for spending his time on creating this video. Thank you, Adam. And you can let us know if you have learned something new or if you found this video useful. Leave your comments. Once this video will get 10,000 views, we will go through them and we will pick up one winner for the book and one winner for the board. If you win, we will contact you. I can leave message or something like that. I can comment on your comment. If you like this video, don't forget press like button. If you would like to see more videos like this, don't forget to subscribe. I would like to thank you very much for watching and see you next time. Bye.